Okay, so chapter 14, acid and bases. Acid properties and examples. Acid have the following properties. Acid have a sour taste. Acid dissolve many metals. Acid turn blue litmus paper to red. And here's the picture of the litmus paper, and this part is in the acid solution, so it become red. Example of acid is hydrochloric acid. So this is the molecule of hydrochloric acid, HCl, and this is the model for the HCl. So this green is the Cl atom, the white is the hydrogen atom. Hydrochloric acid is found in most chemistry laboratories. It is a strong acid. It is used in industry to clean metals, prepare and process food, and refine metal ores. Hydrochloric acid is the main component of stomach acid. Hydrochloric acid helps break down food, and it kills harmful bacteria that might enter the body through food. Another example of acid is the sulfuric acid and also the nitric acid. So their formula and structures is shown in these two pictures. The left is for the sulfuric acid, the right is for the nitric acid. Sulfuric acid is the most widely produced chemical in the United States. Annual U.S. production of sulfuric acid exceeds 36 million tons. Sulfuric acid and nitric acid commonly used in the laboratory. Sulfuric acid and nitric acid are used in manufacture of fertilizers, explosives, dyes, and glue. Both sulfuric acid and nitric acid are strong acids. Sulfuric acid is contained in most automobile batteries. Another example of acid is acetic acid. Here's the picture and formula for the acetic acid. Acetic acid forms in improperly stored wines. The word vinegar originates from French vin, which means sour wine. Acetic acid is an example of carboxylic acid. It's organic acid. Acid contains the COOH groups of atoms known as the carboxylic acid group. So here is the carboxylic acid group, COOH. This bond is bonding to something else. So the carbon double bond to the O, and the single bond to the oxygen, then oxygen single bond to this H. This H will be the acetic H. Acetic acid is a weak acid. There's a few more carboxylic acid. One is the citric acid, and the other one is the malic acid. There are formula and model is given in those pictures. You can see in this citric acid, there will be 3 carboxylic groups. So this is the one, this is the one, this is the one. In malic acid, there will be 2 of those carboxylic acid group. One here on the right, one here on the left. This OH is the alcohol group, not the acid group. We often find carboxylic acid in substances derived from living organisms. Other carboxylic acid, including citric acid here, the main acid in lemon and the limes, and malic acid, an acid found in apples, grapes, and wine. Both citric acid and malic acid are weak acid. bases, these properties and examples. Base have the following properties. Base have a bitter taste. Base feel a slippery feel. Base turn red litmus paper to blue. See this red litmus paper. This part is in basic solution and it becomes blue. Base feel slippery. All of those consumer products contain bases. Here are some of those common consumer products. Yeah, one example is those Drano to clean the drains in the sink or bathtub. Bases feel slippery because they react with oil on your skin to form soup-like substances. Soup itself is basic, and its slippery feel is a characteristic of bases. Some household cleaning solutions, such as ammonia, are also basic and have the typically slippery feel of a base. Base taste bitter. Bases are less common in food than acid because of their bitter taste. Our aversion to the taste of base is probably an adaptation to protect us against alkaloid, which are organic bases found in plants. Alkaloids are often poisonous. The active component of Hemlock, for example, is the alkaloid choline, and their bitter taste warns us against eating them. And has a molecular formula and structure of choline. The death of Sucrates was by choline poisoning, as shown in this paint. Some food contains small amount of base. Caffeine is acidic overall, but the base is present in coffee, such as caffeine, impart a bitter flavor. And here is the structure and molecular formula for caffeine. Base examples, sodium hydroxide, potassium hydroxide, and sodium bicarbonate. Sodium hydroxide and potassium hydroxide are found in most chemistry laboratories. They are used in processing petroleum and cotton and in soap and plastic manufacturing. Sodium hydroxide is the active ingredient in products such as Drano that work to unclog drains. Sodium bicarbonate can be found in most homes as baking soda and is an active ingredient in many antacids. When taken as antacid, sodium bicarbonate neutralizes stomach acid, relieving heartburns and sour stomach. The definition of some of those acid base, first, Arrhenius definition of acid. According to Arrhenius, acid, some of those substances produce H+ ion in aqueous solution. Here is a picture for HCl. So if you put HCl in water, it produces H+ ion, Cl negative ion. So H+ ion will give the solution the acidic characteristic. Okay, so again, HCl is a covalent compound and does not contain ions. In water, HCl ionizes to form H+ ion and Cl negative ions. So the process is, or the equation for this process is written as HClAq, which means you put HCl in water. Once you put that in water, the water will separate the H+ from the Cl negative. or separate the H atom from the Cl atom. And as a result, we have two ions. The H plus ion are highly reactive. In aqueous solution, they bond to water molecule according to the following reaction. So H plus H2O, which is the water molecule, produce H3O, H3H, and 1O plus. So the H3O plus is named as hydronium ion. In water, H plus ion always associated with H2O molecules. Chemists often use H plus AQ and H3O plus AQ interchangeably to refer to a hydronium ion. In the molecular formula of an acid, we often write the ionizable hydrogen first. Often, but not always. So therefore, we write the formula for formic acid as HCHO2. So this first highlighted red H atom is so-called ionizable, which means if you put this molecule in water, so most likely this H can get apart from this unit, become H plus. Then there's another H. That H is non-ionizable H. We represent the structure of formic acid with its structure formula as this. And here you will see more clearly the COOH group we talked about in the previous slide, or the carboxylic acid group, the COOH. So therefore, this H is the ionizable hydrogen. The structure formula indicates how the atoms are bonded together. The molecular formula indicates the number of each type of atom. So it's very useful to know what are the structure formula for some of those given compounds. Arrhenius definition of bases, and here is a picture. We have NaOH. We know NaOH is strong base because if you put NaOH in water, what we get is Na plus ion, OH one negative ion, OH one negative ion, make the solution have the characteristic of basic. The base, according to Arrhenius, a base produces OH negative ion in aqueous solution. So OH negative ion is the hydroxide. NaOH is an Arrhenius base because it produces OH negative ion in solution. NaOH is an ionic compound and contains Na plus ion and hydroxide ions. When NaOH is added to water, it dissociates into its component ions. Some molecular compounds contain an OH group, such as methanol CH3OH, do not dissociate in solution and therefore do not act as a basis. Under the Arrhenius definition, acids and bases naturally combine to form water, neutralizing each other in the process. So you can write a net ionic equation as H plus aqueous plus OH negative aqueous produce H2O liquid. Another definition of acid base is Bronsted-Lowry definition. So according to Bronsted-Lowry, acid is a substance that donate proton, or acid is a proton donor. A base is a proton acceptor. So what do they mean by proton? Proton means H plus. The Arrhenius definition does not apply to non-aqueous solvent. The Bronsted-Lowry definition of acid base applies to a wide range of acid base phenomena. This definition focuses on the transfer of proton H plus ion in an acid-base reaction. Since an H plus ion is a proton, a hydrogen atom with its electron taken away, so that's a proton. This definition focuses on the idea of a proton donor and proton acceptor. According to this definition, HCl is a Brown-Lowry acid because in solution it donates a proton to water. The following equation represents that process. We have HCl aqueous plus H2O liquid produce H3O plus and Cl negative aqueous. So in this process, going from left to right, you can see this HCl donating the H plus or lost the H plus. Therefore, we say HCl is the acid. This definition more clearly accounts for what happens to the H plus ion from an acid. It associates with a water molecule to form H3O plus, a hydronium ion. The Bronsted-Lowry definition works well with bases such as NH3 that do not inherently contain the hydroxide ion, but still produce hydroxide ion in solution. So we can see this equation: ammonia NH3 aqueous plus H2O liquid produce NH4 plus and hydroxide. So in this process, this NH3 take one H plus away from water, it turn into NH4 plus, then make water turn into hydroxide. Therefore, we say in this reaction, this ammonia, this NH3 is a Bronsted-Lowry base because it accepts a proton from water. So in the reaction between HCl and H2O, HCl is the proton donor and H2O or the water is the proton acceptor, so water is the base. In the reaction between NH3 and water, H2O is the proton donor acid and NH3 the proton acceptor is the base. So in these two reactions, we have water in one reaction that behave as base. In other reaction, water behave as acid. And also the last equation show you if you have a base and then the base will produce the conjugate acid. So this is base NH3. So if the base accepts the H plus, then the product become the conjugate acid. Vice versa, if the something is acid and it's donating the H plus, then itself turn into the conjugate base. So we say those are the conjugate pairs. The conjugate pairs. So base and conjugate acid, acid conjugate base. So here in the one practice, want to classify matter. In each reaction, identify the Bronsted-Lowry acid, Bronsted-Lowry base, and conjugate acid, conjugate base. The first one is the reaction between H2SO4 and water, turn into H3O plus and HSO4 1 negative. So in the reaction, we can see this H2SO4 donates a proton to H2O in this reaction. H is the acid because it's the proton donor. After H2SO4 donates the proton, it becomes HSO4 1 negative. That will be the conjugate base. Since H2O accepts the proton, it is the base, the proton acceptor. After H2 accepts the proton, it becomes H3O plus, the conjugate acid. So here we summarize. H2SO4 is the acid, it produces conjugate base, and water is the base, it produces conjugate acid. The second part of the question is we have HCO3 negative H2O produce H2CO3 and OH negative. So on the left side, we have H2O. Since H2O donates a proton to HCO3 negative in this direction, going from left to right, it is the acid, the proton donor. After H2O donating the proton, it becomes hydroxide, the conjugate base. And since HCO3 negative accept the proton, it is the base, the proton acceptor. After HCO3 negative accept the proton, it becomes H2CO3, the conjugate acid. So we summarize, see, HCO3 negative is the base going from left to right. Then it produces the conjugate acid H2CO3. So water on the left act as acid because it donates the H plus. Then it turns into the conjugate base hydroxide. And the reaction of acid base pretty much is the neutralization reaction. When an acid and a base are mixed, the H plus from acid combines with the hydroxide from base to form H2O. Here's one example. We have HCl, Sa is the acid, KOH is the base. So these two acid-base reaction produce H2O and then KCl. We call those ionic compound the salt. Acid-base reaction generally forms water and salt. An ionic compound is called the salt that usually remain dissolved in the solution. The salt contains the cation, so the cation from the base, and the anion from the acid. So in this salt, K is cation come from the base. Cl is anion come from the acid. The net ion equation for many neutralization reactions is H plus Aq plus OH negative Aq produce H2O liquid. Okay, so writing equation for neutralization reaction, write a molecular equation for the reaction between aqueous HCl and aqueous CaOH2 calcium hydroxide. So the solution is you first identify the acid and base and write the skeletal reaction showing the production of water and the salt. The formula for the ionic compounds in the equation must be charge neutral, as we see in section 5.5. So we write HCl because that is the given one reactant, so that's the acid, Ca and parentheses OH and parentheses 2 aqueous is our base. So we see they produce H2O, then we take the cation from the base and anion from the acid produce the salt to neutralize the charge because Ca is 2 plus Cl is 1 negative. So we need 2 Cl to neutralize the charge. This is the skeletal chemical reaction equation. So you want to balance the equation by using the coefficient. Notice that Ca OH2 contain 2 mole of OH for every 1 mole of CaOH2. So therefore, it requires 2 mole of H plus to neutralize. So therefore, we will put 2 for the HCl. If you put 2 for HCl, that means we can see 2 H2O liquid. So acid-base titration is a way to quantify the amount of acid or base in a solution, which is pretty much using the acid-base reaction. Then you control how much you mix, and so that will be the titration. Solution stoichiometry can be applied to a common laboratory procedure called titration. In titration, a substance in a solution of known concentration is reacted with another substance in the solution of unknown concentration. The unknown concentration is calculated from the titration data, its own volume used and the volume used and concentration of the other substances. For example, an acid-base titration, the concentration of the base can be calculated from its own volume used and the volume used and concentration of the acid, vice versa. So here we see the picture for the titration. Usually you will see these two solutions. One solution in one container, the other solution in the other container. And here the container we use is a flask. You can also use a beaker. Typically, you will use this long skinning called the burette for the other reactant. So you control how much you add them together until they are both used up. So that's called the equivalent point. Okay, so again, here we're starting with acid in the flask. We don't have any base. So we're just adding the base gradually. So adding base will use acid, adding base use acid. You just control until you adding enough base, use up all the acid in the flask, then you have the equivalent point. So from those data, you can calculate the concentrations. So in titrating this example, we slowly add a solution of NaOH with known concentration to the solution of HCl with unknown concentration in the flask. So before you starting the adding, you control or you measure how much acid you have, even though you don't know the concentration, but you know how much volume of the acid in the flask. So then you know the concentration of the base, and then if you adding slowly, you will see when it's all used up by the acid, and you stop adding, you will see how much NaOH you use. So from the volume of NaOH you use and the concentration of NaOH itself, you can calculate the concentration of the acid because you know the volume of that. At the equivalent point, neither reactant is present in excess and both are used up or both are limited. The number of moles of the reactant are related by the reaction stoichiometry. So as the hydroxide is added, it reacts with and neutralizes H+, forming water. At the equivalent point, the point in the titration when the number of moles of OH added equal to the number of moles of H+ originally in the solution, the titration is complete. The equivalent point is usually signaled by an indicator, which is a dye whose color depends on the acidity of the solution or use pH meter. So in most laboratory titration, the concentration of one of the reactant solution is unknown. The concentration of the other one is precisely known. By carefully measure the volume of each solution required to reaching the equivalent point, the concentration of the unknown solution can be determined. And in this titration, NaOH is added to HCl again. So here, when the NaOH and HCl reach equivalent proportions, one of OH, one negative for every one more of H+, the indicator here is phenolphthalein, which is colorless in acid and become pink when the pH higher than 8. So it's when this signal happens, that means we don't have any acid base in the flask. See, both are used. So signal the equivalent point of titration when we have see the red. Phenolphthalein is a common indicator that is colorless in acidic solution and the pink in basic solution. Now we will see some of those examples of the titration. So here the titration of 10.00 ml, which is a milliliter of HCl solution of unknown concentration. So we know our acid, we don't know the concentration, but we see how much we put in the flask, we know the volume. And we say to use up all those acid, we need 12.54 milliliter of strong base, which is NaOH. Then we know the concentration of the NaOH used is 0.100 molar to reach the equivalent point. So from those data, we can calculate the concentration of the unknown HCl solution. So to do that, we'll first write the balanced chemical equation for the reaction between acid and base. So we see acid is the HCl, base is the NaOH, product is H2O and NaCl. Then we balance the equation is balanced. So then another step will be to calculate more of the HCl, which means calculate the mole of HCl from the data of titration. So what we know is we know the milliliter of NaOH used, and then we know the concentration of NaOH. So we're using this is 3-step to calculate mole of HCl. So we know the 12.54 ml of NaOH. We need to use this conversion to converting from the ml to the L. So after we get the liter, then we'll use this concentration. So remember, this concentration can always be written as a fraction whenever you see the capital M. So that becomes 0.100 mol over 1L. So we multiply this those quantities, we'll see the cancellation of the L and the cancellation of the ml will get more mol and NaOH. But we want to get the mole of HCl. We will use the mole ratio, which is the coefficient ratio in the balance equation. From the equation, we can see there's no number in front of HCl, so that means 1. And no number for NaOH, that means also 1. So therefore, we have 1 mol HCl over 1 mol NaOH. So we can use this mole ratio to converting the mole of NaOH to the mole of HCl. So once we get more of HCl, we calculate molarity by using the definition of molarity. Molarity, the capital M equal to mol over L. Okay, now we will apply our map. So the first step is calculate mole of HCl. You see in this process, we cancel out all the unit. We only have 1 unit left over, which is the mol HCl. So that is what we want. And we calculating by dividing and multiply those numbers. We get 1.25 times 10 to the negative 3 mol HCl. Okay, so now we get one quantity for the molarity. The second step is just calculate the molarity. So we know how much volume of the HCl used. In the question, it's given 10.00 ml. Then you know 10.0 ml is 0.01000 L. Okay, so this how we get this L, this volume. And this number comes from step 1. So therefore we get 0.125 capital M, which is a molar or molarity. So now solve the problem. And so we also know acid base can be strong, can be weak. For example, hydrochloric acid, HCl, and hydrofluoric acid, they are both acids, they appear similar, but there is an important difference between these two acids. HCl is an example of a strong acid, so that means the strong acid completely ionized in solution. HF is a weak acid. The weak acid that does not completely ionize in solution. And see, this picture will tell the complete or incomplete. So the left one is HCl. When HCl dissolves in water, it completely ionized into H3O plus and Cl negative one ion. So therefore, we don't see any those HCl remaining after it dissolves. And here is the formula, here is the picture. So we can see this is the HCl, the green one is Cl, the white one is H. So after we put this in water, we don't see the white and the green together anymore. They all separated. So ideally, that's the truth. Right. So therefore, we use one arrow indicates the complete ionization. Just one arrow pointing from left to right. Now you compare the other weak acid, which is HF. When HF dissolves in water, only a fraction of the dissolved molecule ionize into H3O plus and F1 negative ion. The solution contains many intact HF molecules as shown in this picture. Left picture just show you the molecular formula. The right picture show you the model. So you're starting with either one. Let's see the right one. We have the H, the white one is H, the green H1 is F. So this is a molecule. You put that in water because this is the weak acid, and then most of them intact. They do not break apart. So you still have the HF, HF, and this picture just show you out of 4, only one of them separate, become ion, even though they're not the right proportion. That means always like 1 out of 4 for the HF do that, just as illustration here. All right, so therefore we use 2 arrows, one arrow pointing to right, the other arrow pointing to left, which means this process is not completely, it's only partially. So this table gives us some of the common strong acid, HCl we saw before, and also HBr, HI, not HF. Then we have the nitrate, perchlorate, and sulfuric. In this class, 6 substances are considered strong acids in aqueous solution. 5 of these 6 acids and table are monoprotic acid. Acid contain only one ionizable proton. Mono, the prefix mono means 1. So monoprotic, 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 and monoprotic. And there's only one diprotic. Di means 2. So that means to the most, the sulfuric acid can give 2 H. So that diprotic acid means an acid contain 2 ionizable protons. An ionizable proton is one that becomes H plus ion in solution. And here are some of the common weak acids. We saw some of them before. For example, the HF we just saw on the last few slides. Acetic acid, carboxylic acid, formic acid, and some of those inorganic acids like sulfuric acid, carbonic acid, and phosphoric acid. There are many weak acids, some organic and some inorganic. Most carboxylic acid are weak acid. 2 of the weak acids shown in table 1 are diprotic and 1 is triprotic. You probably can see which one di. So these 3 are mono, these 2 are di, this one triprotic. So sulfuric acid and carbonic acid are weak in both of their ionizable proton, and phosphoric acid is weak in all 3 of the ionizable protons. So phosphoric is the last one. It has 3 H, can be ionized. Sulfuric acid listed in the last slide is the strong acid, is the diprotic acid that is strong in its first ionizable proton, but weak in its second ionizable proton. So here we want to determine the H3O plus concentration in acidic solutions. So determine the H3O plus concentration in each solution, use equal, less than, or larger than. So we know that depends on the strength of the acid. So if we have a mono protic strong acid, like this first one, so therefore we can say equal. So since HCl is a strong acid, it completely ionized, the concentration of H3O plus equal to the concentration of HCl is mono strong, so that's why we say equal. For the Second one, this is a way of write acetic acid. We know acetic acid is a weak acid, so it's partially ionized. The calculation of the exact concentration is not in this class, so we will not do the calculation. But we just say because it's a weak acid, it's not 100% give you the H plus, therefore we will say it's less than the H plus concentration or the H3O plus concentration is less than the concentration of the given acid, which means the whole unit. So the whole unit 3.0 molar. Therefore, this is the weak acid. We will see the H3O plus is less than 3.0 molar. And the last one is the strong acid is monoprotic, so therefore it will be equal. Okay, so again, since HNO3 is a strong acid, so if it's a strong monoprotic, it completely ionizes the concentration of the H3O plus is same as the acid. The acid concentration is given. So when you give this problem, this concentration referring to this acid. But here the question is what is the concentration of the H3O plus? So therefore, depend on acid strong or weak, and if they are strong, they are monoprotic, so they are equal. Otherwise, depend on the question. For the second one, the acetic acid, which is the mono weak acid, so therefore we see less. And for the other two, A and C, they are monoprotic strong acids, so they are the same. They are equal. A strong base is the one that completely dissociates in solution. And here, so here are a few examples of the strong bases: LiOH, NaOH, KOH. So for these three metal hydroxide, they give you one hydroxide. For each one unit, there is one OH. For these three on the right, they will give you two OH. So for every one of this, it will give you two OH. So again, an NaOH solution contains no intact NaOH. It has all dissociated into Na plus and OH1 negative. When NaOH dissolves in water, it completely dissociates into Na plus and OH1 negative. Here the formula has a picture. Either way, show you we don't have any NaOH together, so they all separate. Weak base is analogous to a weak acid. Unlike a strong base, they contain OH negative and dissociating water. The most common weak bases produce hydroxide by accepting a proton from water, causing the water to form hydroxide ion. So they are, if they are weak base, we will use two arrows from left to right or from right to left. So here just a generic name just called B, which is standing for base, not for boron. It's just B for base. So that's a base and react with water. So the base accept the H plus from water become BH plus, and then water become OH negative. In this reaction, B is a generic name for weak base, not boron again. So the B can be NH3. So therefore, when NH3 dissolves in water, it partially ionized to form NH4 plus and OH negative. However, only a fraction of the molecular ionized, most molecules remain as NH3. And this table show you some of those common weak bases. We saw ammonia, and then most of them contain the nitrogen atom. Then the last one is the bicarbonate, HCO3 1 negative, that don't have the nitrogen. There are many weak bases. Organic amines are weak bases. So this is the organic amine, and they are all some of those molecules have the nitrogen atom. And here are the formula or the equation when they reacting with water and they behave as a base. And they all produce OH negative, OH negative, OH negative, OH negative, OH negative. And depend on the acid strength, we know how to figure out the concentration of H plus. And similarly, depend on the strength of the base, we can get some idea like use equal, less than to see the concentration of hydroxide. So the first question is 2.25 molar KOH. So what will be the concentration for hydroxide in this solution? We know the KOH is from a base. So for each one KOH, it will give you one OH negative. So therefore, we see the concentration of hydroxide is 2.25, which is same as the concentration for KOH. So here you want to see the difference between the concentration for KOH and the concentration. I mean, conservatively, we'll see the difference, even though the number here are the same. So therefore, we see OH negative concentration equals to 2.25, even though the 2.25 initially conservatively referring to the concentration of KOH. So the second base is a weak base, and we know it will not give you the same number as the concentration for this molecule. It will be less than, right? Because it's a weak base. So therefore, even though we in this class we don't do the calculation, but we just say it's less than this 0.35. It's much less than. Then the last one is a strong base, and but it's a kind of a strong base in some sense different than this strong base, because in this strong base, there's only one OH for one formula unit. In this strong base, it will give you two OH and completely give you two OH. So there's a 1 and 2 ratio in this base. So therefore, the concentration for the hydroxide come from this two. You will multiply the concentration of the hydroxide by 2. Okay? So therefore, you get 0.050, even though the concentration for the base formula 0.025. From each formula, you get 2 hydroxide. So 2 hydroxide. So therefore, you multiply the concentration of the base formula by 2 to get the concentration of hydroxide. So we can conveniently to use some new number to see the acidity and the basicity of a solution, which are pH and pOH. So pH just mathematically equal to negative log the concentration of H plus. So log is the time-based logarithm function. So just use your calculator. If you know the concentration of H plus, which should be the molarity, you take the negative log, you will get pH. If you know the concentration, the molarity concentration of hydroxide, you take a negative log of the concentration of hydroxide, so we will get pOH. And these two are connected. And so pOH plus pH equal to 14. And also, you know, at 25 degrees Celsius, if the pH less than 7 for a solution, then you have acidic solution. If the pH equal to 7, that means you have a neutral solution. If pH larger than 7, then the solution is basic. And therefore, the pH scale really make the comparison much neat and easier. Typically, the pH value is like 0 to 14. If you compare the number for the H plus molarity, you will see a huge range, so not convenient. So here we want to calculate the pH of each solution, then indicating whether the solution is acidic or basic. So what you have is the concentration of the H3O plus. We know we can use H3O plus and H plus in the same way. which means if this concentration is for H3O plus, then it's the same as for H plus. So in the equation, we write pH equals negative log H plus. Therefore, we can use the number for the H3O plus. We just plug in into the calculator. So again, this log is time-based logarithm, and we put this information in the calculator. We get negative 3.74, so therefore get positive 3.74, which means the pH is less than 7, so therefore it's acidic. For the second part of the question, we have the H3O plus. Again, we can use that as H plus, and we put in the calculator, we get negative 8.14, so we get positive 8.14, and which is more than 7, so therefore it's basic. You can do the reverse by just do some of the simple math work. If you know the pH, you can calculate the molarity or the molar concentration of H plus or H3O plus. So we'll use this 10 to the negative x function in your calculator. So mathematically, or the equation, we know the pH is written as negative log H3O plus. We will plug those numbers in, so we know the pH, so 4.8. And then what you do, you will multiply or divide both sides by -1, right? So negative become positive on the right. Then this positive 4.80 become negative 4.80. Then you will use this function because this time-based exponential function and then time-based logarithm function are the inverse function of each other. So you take the or you use a time-based logarithm on the left, you will get 10 to the negative 4.80. If you use time-based logarithm, time-based exponential on the right, so you get 10 to the power of log z H3 plus. Then what happens is this exponential function, logarithm function, they inverse each other. That means they cancel. That means kind of they don't do anything. So you do something like divide by something, then you multiply by something, so that's inverse each other. Okay. So that's cancel out. So therefore, we still have this side 10 to the negative 4.8. Then the 10 and log cancel out. That means they don't do anything. So you are left over with H3O plus. And then use your calculator, just calculate what is the 10 to the negative 4.80 power. So the calculator can do that. So therefore we get 1.6, 10 to the negative 5. And so another interesting solution in the buffer. In the buffer solution, we will resist the pH change, and we remedies the pH change. Buffer contains significant amount of both weak acid and its conjugate base. The acid neutralized added on base. The conjugate base neutralized added on acid. And for example, the human blood has a buffer. In a healthy individual, the blood pH is between 7.36, 7.40. It's very narrow range for the pH. Therefore, there's a few like we need a buffer in human bodies. There's a few buffers. So one of them was the carbonic acid and bicarbonate. There are also other like the hemoglobin and so on. So the blood pH, if the blood pH would drop below 7.0 or about 7.8, and then that will be fatal. In the, let's say in this one example buffer, in the acetic acid, sodium acetate buffer cysteine, there is the acid, which is the acetic acid, and there's the base, which is the acetate ion. When base is added, the acetic acid will react. So Again, we have a buffer. That means we have the acid base. If you adding some acid, adding some base, then what the buffer do is try to neutralize what's adding on, so minimize the pH change. So let's say we have this buffer, and we're adding a strong base. If you're adding strong base to water, your pH will go up very quick. But if you're adding a strong base to a buffer, your pH will go up a little bit. But if you continue adding, then you will destroy the buffer, then it will go up very quick also. So when acid is added, then the base in a buffer will neutralize added on acid. So our buffer, the base is the acetate. But you cannot only get acetate, so therefore we need to see the counter ion. So acetate is negative ion, the counter ion is Na, Na is plus. Even though Na is just spectator. So therefore, when you're adding a strong acid, so this like a weak base turn the acid into a weak acid. So in that sense, the pH will not go down too much. And the acid consume any added base, the base consume any added acid. In this way, the buffer resists pH change. So again, they not really totally take them away. They just change, like for example, from a strong acid into a weak acid, changing the added on strong base into a weak base. So in that sense, you will not see too much pH change. In this cartoon, and we can see we have a buffer. Our buffer will have these two components. Okay, so this component is our acid component of the buffer, and then this component is our base component of the buffer. We need this spectator ion to make our sodium acetate, because you cannot only have acetate. So just remember we have these two components, the weak base, weak acid. Now we will see what will happen if you adding some of this strong acid or adding some of this strong base. In this picture, we see we adding some of those strong acid. Strong acid will give the H plus. If you don't do anything, then your pH will drop very quick. But if you have a buffer, so the weak base in the buffer will take in the H plus, it turn into a weak acid, turn into this. So even though it's turned into a weak acid, but the acid is weak, you will not 100% ionize into H plus. Therefore, it really like neutralize most of the H plus you add on, and vice versa. If you adding some of those strong base, and if you don't do anything else, then your pH will go up very quick. But if your buffer, so the weak acid in the buffer react with the add-on strong base, and turn the strong base into this weak base, then you see you still have base, but you turn a strong base into a weak base. That means the weak base will not give you that much of OH, because OH is basic. So therefore, it will make the pH change to as small as possible, depend on your weak acid and weak base, and depend on how much you have. Okay, so this is for this chapter. This is the end of this